Hi everybody, this is the fifth lecture and final lecture of this first unit. Therefore, this is the final stuff that will be on the first exam. And let's see how long this video is. I'll sort of remind you, this was mentioned in the either the welcome video with the just welcome to the class, or it was in the syllabus and course overview video, is that some lectures could be quite long. Remember that this class would be meeting for a long time, each class session. And so what I'll say is there's two things. One is if there is a long video, you're in charge of it. So it's not like we're in class and you have to sit there until somebody tells you have a break or something like that. You can plan these things out yourselves. And so for one, when you start a video, you can see how long it is. And then maybe you can make a plan based on how long the video is. Or you could just simply go, and then if you feel tired, you feel like you're not quite absorbing things like you were earlier in the video session, is just take a break. And the break could be maybe coming back the next day if it's just too much, or if you're doing it late. And so what I'll say is that you can take charge of when you want breaks for the video. Just pause the video, write down the time that you paused it, and just come back either after a few minutes break, or come back later that day, or come back another day. That's all totally fine. So don't feel like you have to watch a video all at once. You're in charge of your time. I might make smaller videos. This is mainly due to technical stuff. So sometimes when there's internet problems, it can interfere with the recording, and then I'd have to re-record everything. So I may piece up the videos a bit more, but let's see. Regardless, you can take breaks whenever you want. And I think that's a very individual thing too. So it's not like everybody should take a break after 45 minutes. Maybe some people could do it for a half hour, or maybe some people can do it for an hour and a half. So it's really up to you when you want to take breaks. Okay, so let's start with this final lecture that's in the first unit. So we'll be on the first test. So these first 5 lectures is the material for the first exam. And I will post on Canvas the study guide for the first exam fairly soon, at least by the beginning of early in the week usually. So we're going to do standard scores here, and I just sort of said this. This is the last material for the first exam, essentially chapters 1 through 5. You can read chapter 6 if you want for the exam, but I think chapters 1 through 5 are the core ideas. And with this lecture, we're actually making a transition from descriptive statistics. So descriptive statistics was basically the frequencies, the central tendency measures, and variability. Now we're moving into the territory of inferential statistics. So remember, inferential statistics is testing hypotheses, taking the data, the findings from your sample, and making conclusions about a population. So inferential is you're taking the findings from the sample and you're making inferences, conclusions about the population. So we studied this group of people. What does this group of people tell us about the population? So it could just say about humans in general. And basically, what we're going to be doing here is the first step. So this is the first of various steps we're going to take to bridge to inferential statistics. So inferential statistics will take us the rest of the semester, actually. We'll look at different techniques, but the philosophy, the thinking, the reasoning behind inferential statistics is really based on what we're going to talk about today and what we're going to talk about just after the next exam. So we're going to start off with sort of very concrete things. After the exam, we'll get to a little bit more theoretical things. And In inferential statistics, we often make statements in terms of probabilities. So we know that a sample can't fully represent a population, and therefore when we make conclusions about a population from a sample, we have to make these statements, these conclusions, in terms of probability. So what we found in our sample, we're 95% sure that you would find this in many samples from the population is basically the reasoning behind it. And we'll get into this more specifically as we get into the semester. And so what's really nice is that probability statements that we use in inferential statistics are directly tied to a perfect normal distribution. So remember, the perfect normal distribution is the one that's symmetrical. It has one mode in the middle, and there's more scores in the middle, and there's fewer scores at the extremes on both ends, both higher and lower. And what's nice about a perfect normal distribution is that it has certain properties that the percentages of scores of people under various parts of the normal curve are the same for every single normal curve. So if you're not getting this yet, don't worry. We're going to be talking about this for at least 2 lectures, this lecture and then the one after the exam. And so what's really nice, again, is the perfect normal distribution has specific percentages of people or of scores under each part of the curve. And we'll talk about this a little bit more specifically in a bit. But what you want to use is you want to get your book. If you have your book, you can use the normal curve distribution. I think I have the appendix referred to later in the PowerPoint, or you can use this link. So you see this link, and it will say a Z table. So if you don't have the textbook, or you go to the textbook and you see the Z table, but it looks overly complicated, you're okay using this. So this Z table you will be using for this lecture, the next homework, and the exam. And we'll get into what this is specifically in a bit. I think I might have to expand this a little bit and give some free advertising here, thanks to Google. But basically, if you look here, there's all these little numbers underneath this thing. And we'll get into how to use this specifically in a bit. But all these little numbers are the percent of people in the curve. So you see a little shaded part here. This little shaded part, you can look up in the table depending on the number that you calculate, and we'll go over that again. And you can find out how many people are underneath that part of the curve. So again, this is just starting out, so I'm just getting your feet wet, and we'll do many examples of this soon. So I've already kind of mentioned this, is that the normal distribution is very important in statistics because in a perfect normal distribution, there's stable percentages along the curve. And so at different parts of the curve, there's different percents of people, and this is true for every single normal distribution. So that's why it means it's stable. It means regardless of the kurtosis, regardless of various things. I think kurtosis is the only thing that can vary for a normal curve. So you could have a platykurtic, you could have a mesokurtic, you could have a leptokurtic normal curve. It doesn't matter. As long as it's a normal distribution, a perfect normal distribution, regardless of whether it's peaky and lepto or whether it's flat and plata, it doesn't really matter. There's certain percentages that are always going to be true for every single normal curve. And that's an important thing, because if they would change, if percentages change for every normal curve, we couldn't actually do research mathematically, because we'd never be able to make probability statements, because every normal curve has these properties we're going to talk about that allows us to say, based on our sample, how confident are we that these findings apply to the population. If this wasn't stable, if a leptokurtic curve had different probabilities under the curve versus a platykurtic, you could just throw out research because you would never be able to make inferences from a sample to a population. At least not one where we could say, we are very certain that the probability that the sample's findings applies to the population is this percent. And so what we're going to do is we're going to start off in a more sort of hands-on way. We're going to play with the normal curve, and we're going to start calculating some of these percentages just to sort of illustrate in a very hands-on way what's going on. So normal distribution, we've already talked about that. It's symmetrical. It has one mode, and there's more scores, more people's scores in the middle of the distribution, and fewer people's scores on the high end and on the low end. So let's just think of IQ. Not that I'm a big believer in IQ. IQ is not measuring any sort of biological or other types of innate intelligence. It's just a measure of things that you've been exposed to and have you learned those things. But there's a big assumption about kids are exposed to the same things. So if kids have different cultures, then this idea that kids are all exposed to one thing is fallible. We can't really stand by that. But let's use IQ anyway, because people kind of know what it is. So, if you're talking about IQ of 100, I didn't choose IQ. I didn't really look at these numbers here because I don't really look at the numbers on the bottom. I just care about the shape of the curve. But 100 is the average IQ. It just basically means the stuff that you could do is exactly equal to all the stuff that people can do that are of your age. So if you're talking about children especially, so you can do exactly the same amount as every 8-year-old if you're 8, but you can't do any more, and you don't do any less. You just do what every 8-year-old can basically do. You don't do more, you don't do less. You're at 100 for an IQ. And so if you get into the high IQs, there's very, very few people that have very high IQ. You don't have to look at this thing, but basically, I'm calculating this in my head. There's very, very few people who have IQs above 145. Conversely, there's very few people who have IQs lower than, I'm doing a calculation, so if it's 45, you have to take 100 minus 45, that's 55. So there are very, 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 very few people who have IQs less than 55. So more in the middle, a lot of people around the average, slightly above average, slightly below average, and very few people who are far away from the average on the high end, and very few people who are far away on the low end. And this lecture, I think, is a good one where if you know what's going on, you can speed up. So I'm just repeating things to try to sink things in. But if you know it, and you can just watch this at twice the speed, or you can fast forward to a certain point on the video. So we talked about that. There's one mode. It's symmetrical. The same amount of scores are on this part of the curve as they are on the other part of the curve. If you cut the normal curve in half, they're exactly equal shapes, the lower and upper half. And it has a bell shape, so more scores in the middle, fewer on the ends. Okay, so here's our first step into their stable percentages across the normal curve. And so here the symbols are expressed in population symbols. So here we have the mean. The mean for population is this little u guy. The little u guy is a mu. So the mu, the mean, is right there in the middle. And then standard deviations. So remember, standard deviations, go back. If you don't know what standard deviations are, go back to lecture 4, variability, review that. So remember that the symbol for population standard deviation is this little curly Q guy. Where is he? Right here. So the little curly Q guy. So what this chart is saying, the mean's in the middle. So perfect normal curve, the mean's perfectly in the middle, and it's at the mode, it's at the peak. It's also at the median, so for a standard normal distribution, the mean is also the median, so there's 50% of the scores above the mean, 50% below. And so what this chart is doing is taking a standard normal distribution and it's chopping it up into standard deviations. So if we look here in the green, there's the mean. So it makes a piece where you're one standard deviation above the mean. So there's the mean, and then you go one standard deviation above the mean in that green area. Since it's symmetrical, you can do the same thing below the mean. So there is one standard deviation below the mean right here. So here's the mean. We go one standard deviation above, one standard deviation below. You see below says -1 standard deviation. So that little green part. So what's kind of interesting here is that if you go from the mean to one standard deviation above the mean, there's 34.1% of people. So if we gave an exam in class and it was a perfect normal distribution, 34.1% of people's scores would be between the mean and one standard deviation above the mean right here. Since the normal curve is symmetrical, it doesn't matter whether we go positive or negative, the percentages are going to be the same. So if we go from the mean to -1 standard deviations below the mean, there are also 34.1% of people in that area. So if we gave an exam and we knew the mean of the exam, and it's a standard normal curve, if we know the mean of the exam and we know the standard deviation, we know that there'd be 34.1% of people from the mean to one standard deviation below the mean. And then if we add up these two things, it's 68.2%. So if we add 34.1, it's 68.2. So what does that mean? That means that there's 68.2% of people within one standard deviation of the mean. So 68.2% of people are in the area of the mean plus or minus one standard deviation. And this should make some sense because remember that most of the scores are close to the mean. So one standard deviation is pretty close to the mean. So if we go plus or minus one standard deviation from the mean, more than 2/3 of our sample scores are there because most of the people are close to the mean in the middle. Again, these percentages are the same for every normal distribution, regardless of kurtosis. So we can go further. So we're just going to take slices. So we're not going to go from the mean in this case. We're going to go from one standard deviation above the mean to two standard deviations above the mean. So between one standard deviation above the mean and two standard deviations above the mean, this yellow area, within that band, there is 13.6% of people's scores. Same thing, it's symmetrical. So same thing for below the mean. So if we take this little yellow band and we go one standard deviation below the mean to two standard deviations below the mean, there's also exactly 13.6% of people's scores there. So plus or minus doesn't matter, the percentages are the same because the normal curve is symmetrical. So now if we add 13.6 plus 13.6, that is 27.2. 27.2 plus 68.2, that's what we found, plus or minus one standard deviation from the mean in the middle. Now, if we are talking about plus or minus two standard deviations from the mean, a whopping 95.4% of people's scores are there. So once again, 95.4% of people's scores are plus or minus 2 standard deviations away from the mean. So we've added the green areas and the yellow areas. So you can see we don't have to go out too far. Once we're 2 standard deviations away from the mean, both above the mean and below the mean, already 95.4% of the people are there. So when we say that most of the scores are in the middle, it's not an exaggeration. There's very few scores beyond even 2 standard deviations away from the mean. Then we have this last little part. There's actually 2 little parts. So even this little area here that you would think might be relatively close to the mean, but it's got very few people. So if we take this red area, the red area is 2 standard deviations above the mean in this case, to 3 standard deviations above the mean, this red area. There's only 2.1% of people between 2 and 3 standard deviations. The same thing is true for below the mean because it's symmetrical, normal curve, symmetrical. 2 standard deviations below the mean, this red area, if I can get my cursor going. 2 standard deviations below the mean to 3 standard deviations below the mean. In this red area, there's only 2.1% of people there. So we have shrinking amount of people. There's a lot in the middle. There's fewer, quite a bit. There's almost a third fewer already than when we cross to the yellow. And then when we cross to the red, there's very few people left. So if we take the 2 red areas, the 2 areas from 2 standard deviations to 3 standard deviations above and below the mean, we have 2.1% plus 2.1%, so that's 4.2%. So if we take this little green and yellow area, which was 95.4%, add the 4.2%, this is a little bit off here, so don't worry about it, it's probably rounding. We're not going to worry about one 1,000th of a point. We're not going to worry about that. So now when we add that red area, there's already 99.7% of people who are in the area of plus or minus 3 standard deviations from the mean. So actually, when I was saying earlier about the IQ, that there's very few people who are 145 or above or 55 and below, I was actually using that 3 standard deviations mark for the Wechsler scales. There's also a Stanford Binet, slightly different standard deviations, but for the Wechsler scales, that's what I was thinking of. So there's only 0.3% of people who are either really high, above 3 standard deviations from the mean, or really low, more than 3 standard deviations below the mean. So these percentages are the same for every normal curve. And it just shows us how many people are in the middle and how few people are not even at the extremes. Even if we just get out about 2 standard deviations, there's very few people that far out. So this is what we're going to really look at for this lecture, is we're going to use these percentages that are stable across all normal curves to slice and dice the normal curve to see what the percentages of people are. And what's really nice about this is that if you know the mean and standard deviation of something, you can make some really good predictions. So remember, this is all about predictions. So I'm making these numbers up. I do not know for a fact what the mean of human gestation is. And gestation is from fertilization of the egg to when the baby pops out. And so let's just assume that the mean, the average, human gestation is 9 months. If we know that the standard deviation is 2 weeks, now people can start making probability statements. So now the doctors can start saying that I'm going to be 68% sure that you're going to have a baby within this 4-week time span. So remember, it's plus or minus 2 weeks because it's 2 weeks is the standard deviation. So we have plus or minus. So we're going here, we're going plus 2 weeks, 1 standard deviation above. We're going minus 2 weeks, 1 standard deviation below the mean. Standard deviation is 2 weeks. So now people can start making probability statements about things because the normal curve allows us to do that. So anything that's distributed normally, and most human characteristics are distributed normally, you can make predictions. And people make predictions like this for insurance, for example. So if you get car insurance, your car rate is going to depend on various things, such as the zip code you live, the type of car that you have, what age you are, what's your gender. I don't know if they ask for race or ethnicity. I think they've outlawed that, but I can't claim to know that 100%. And so what they do is for all those characteristics, there's probably a normal distribution in terms of how many accidents you'll have over your lifespan or within the next year. So they have all these data, and they're probably normally distributed. And so they make these probability predictions about what's the likelihood of you getting in an accident, or you as a member of a larger group of all these demographic characteristics of being in an accident, or this many people from that group's going to be in that accident, and they're going to charge you money so they know that they have a lot left over after they make payments on claims that people have. So all of these probability stuffs lie also in business and other areas besides research, because these are very stable probabilities. Okay, so standard scores is the topic of this lecture. And what standard scores is basically saying is that we can't really look at a raw score because the raw score doesn't mean anything. So if somebody comes up to you and says, oh my gosh, I got 100 on the exam, and you go, oh, that's fantastic. How many points was it out of? And they say 300. What was the average for the class? Well, 200. You start saying, well, yeah, that's, oh my gosh, yeah, that's bad. Or somebody comes and says they got 100, and then you find out that there was only 120 points possible. You say, oh, that sounds pretty good, and that the average was, let's say, 80. Then you start saying, oh my gosh, that 100's looking pretty good. And so we can only understand how good a score is if we know the mean and standard deviation of the distribution of those scores. So you don't know if you did well in a class on an exam unless you know the mean average score in the class and the standard deviation. That tells you exactly what your score was, going back to here. So if your score, in terms of where it lies on this, if it's 2 standard deviations or 3 standard deviations above the mean, you're feeling really great. If it's 2 standard deviations, 3 standard deviations below the mean, you're starting to feel pretty horrible. So again, these raw scores, a score on anything doesn't mean anything unless you know the mean and standard deviation. This drives me nuts with IQ. So people often think they know IQs, and then you hear like somebody has, oh, I have 120, it's really high. It's actually not that high. You would be in that yellow area there, so not too bad, but probably nothing to beat your chest and jump around. So if you know statistics, then you know means and standard deviations. You need to know that. You need to know where you lie on the scale. Are you up here? Are you above 98% of the people, or are you above only 2% of the people? So where you lie in a normal curve is much more telling than the raw scores. So z-scores, standard scores, all it does is take a raw score and convert it into standard deviation units. So where do you lie on this curve? So we don't care what your score is, what your raw score is. We care about whether you are 1 standard deviation above, 2 standard deviations above, 1 standard deviation below, 3 standard deviations below. We care about standard deviations. We don't care about the score. So z-scores, standard scores, are expressed in standard deviation units, so we then know where you lie along the curve. Sometimes they call this normalization. Why is it called normalization? It's because it's putting you on the normal curve, the perfect normal curve. And because of that, these z-scores, they're expressed in positive z-scores are above the mean, negative z-scores are below the mean. And so here is exactly the z-scores. So if you have a z-score of 0, that means you got the mean. Whatever score you have, whatever raw score you have, that's the mean. So if the mean score on an IQ test is 100, if you got a raw score of 100 on the IQ test, your z-score is 0 because you're right exactly on the mean. You're right in the middle here. If the IQ test has a mean of 100 and a standard deviation of 15, if you got a score of 115, you would be exactly one standard deviation above the mean. So your z-score would be +1. 15 is the standard deviation. You got 115. You're 15 points above the standard deviation. You're one standard deviation above the mean. I'm not sure if I messed it up, but 15 points is a standard deviation. You're 15 points above the mean. You're one standard deviation above the mean. Your z-score is +1. Same thing for 130. 130, well, that's 30 points above the mean. There's 15 points in a standard deviation. You're two standard deviations above the mean. So if your raw IQ score is 130, your z-score is +2. You're two standard deviations above the mean. You're 30 points above the mean. 15 points in a standard deviation. You have two standard deviations above the mean. Same thing for the negative ones. So if they're negative scores, I know that you got below the mean. So if you got a score of 85, that raw score of 85 on the IQ test is 15 points below the mean. So you're one standard deviation. A standard deviation is 15. You're one standard deviation below the mean. So your z-score is -1. You're one standard deviation below the mean. Same thing for the next z-score. If you got 70, you're 30 points below the mean. There's 15 points in a standard deviation. You're two standard deviations below the mean. You're 30 points below the mean. Your z-score is -2. So the z-score tells you exactly where you are on the normal curve in terms of standard deviation units, because remember, that's what matters. What percent of people are below you, for example, depends on where you are in terms of standard deviation units above the mean, below the mean. And that's what we're doing here. So again, 0 is the mean. Positive z-scores are above the mean. Negative z-scores are below the mean. And the z-scores are expressed in terms of standard deviations from the mean. So here's some other examples. So at the bottom here, so if we have a z-score that is 1.5, so your z is 1.5, that means you're 1.5 standard deviations above the mean. I'm going to actually change this. I should say just from, it should say above the mean. So positive 1.5, you're 1.5 standard deviations above the mean. So you're somewhere around here. 1.5 standard deviations above the mean. So you're somewhere around here. Also, for example, on the bottom there, if your z-score is -2.4, you're 2.4 standard deviations below the mean. So going back to here, so here's two standard deviations below the mean. 2.4 is about here. So you're around this area. So if we know your z-score, we know how many people score below you and how many people scored above you. And what's really nice is that z-scores can be calculated really easily as long as you know what the raw score is, so what somebody got on something, some sort of measurement, could be an exam. And if you know the distributions mean and standard deviation, you can easily calculate their z-score. And here's the formula. So again, don't freak out when you see formulas. Formulas are actually our friends. As long as you know what the symbols mean, it just tells us what's going on. So what is it telling us? Well, we care about how far you are from the mean, right? So our starting point is the top here. This is just saying the z for any score. So xi means any score. We can compute this for any score, any raw score. So xi is the raw score, so what you got on an exam. So the first question we ask is how far are you from the mean? So if you got more higher score than the mean, you're going to have a positive z-score. This all comes from here. If you got a score that's lower than the mean, you're going to have a negative z-score. So the first question we ask is how far in terms of points, how many points were you from the mean? But we've been just talking a lot about, well, raw scores don't matter, points don't matter. What matters is standard deviation. So when we ask how many points you got above the mean or how many points you got below the mean, that doesn't have any meaning unless we standardize the score, standard scores. How do we standardize it? We take this difference, your score minus the mean, we divide it by the standard deviation. So conceptually, it's relatively easy if we think about it. So again, the top is how many points above or how many points below the mean were you? And then the question is, well, we know how many points you got above or below, but that doesn't mean anything. We need to convert that to a standard score. How do we standardize stuff? Through standard deviation. So divide it by the standard deviation of the distribution. So that will give you a z-score. So difference from the mean, and we have to standardize it with the standard deviation. So the formula is relatively simple that way. Let's do some. I'm gonna draw some of these. So I have a piece of paper handy to draw on. So here's a really easy start. So let's take a raw score of 49. So let's say there was a quiz or a test and you got 49 out of it. And then the professor says that the mean of the class was 56, and then you start sweating. And then they say that the standard deviation was 8.1, and you start thinking, well, what does that mean? But if you've taken this class, you know what it means. So all you do is you take your score, 49, subtract that, and that's in points. That's a raw score. Take 49 minus the mean of 56, so 49 minus 56, and you're going to divide it by 8.1 because the points don't matter, standard deviation matters. So we have 49 minus 56 divided by 8.1, your score minus the mean divided by the standard deviation. So it's a negative z-score, so your score, 49, was below the mean, so it's going to be a negative z-score. So we have negative 7 divided by 8.1. That's going to be a z-score, a negative z-score of 0.86. We'll round up to 0.86. And in fact, I think I'm just going to do that right now. And so if we actually drew this, and what I'm going to have you is I'm going to have you draw these things. And so drawing these things is very important for the homework and the exams because it shows your logic, and it also will help you think about the logic. And so I just want to make sure I remember it. It was negative 0.86. And these things don't need to be exact. You know, unless you're a computer, you're going to just basically approximate these curves. And that's totally fine. But it shows your logic. And so I think it's ready to go. And so we have a normal curve. And yours might be better than mine because if I'm drawing by freehand, it's slightly better than this at least. but with this little keypad on my laptop, it's difficult. Remember that in the middle, here's the mean. And why am I saying the mean? Because this is a sample. So we're going to use the symbols for samples. The stuff that we had earlier, that little multicolored chart was in population symbols. But we're going to have samples. So our mean's in the middle. And remember that our z-score was negative 0.86. So that means that your z-score is probably around here. So this is a z of, if I can do the z correct, it's negative 0.86. And this is roughly. So there's probably, very few people, I should say very few, but, not that many people below you. So there was 34.1, I believe, right here. So there's probably 20% or so of people below you. But we'll use the charts later to tell us the exact numbers. And there's more people above you. So negative 0.86 would be roughly here. It's roughly there. Again, I'm not expecting you to make perfect things. But if you drew this, it shows me your logic. It shows me that you know a negative z-score is over here, and a 0.86 negative z-score is roughly around here. So with this chart right away, I can tell that you know what you're doing. And hopefully making charts like that will help you think conceptually about what you're doing also. Okay, so notice on the bottom that it says that one of the nice things about quite a few things that we do in the stats class is that there's ways that you can double check it logically. So logically, you know that your score of 49 was lower than 56. So right away, you know it should be a negative z-score. So if you don't calculate it, if you miscalculate it and you get a positive z-score, you should look and think, oh, logically, that doesn't make any sense because I got a score below the mean. It must have a negative z-score. So make sure that you follow those pieces of logic. When you make a miscalculation, but it's logical, so let's say that you calculated and somehow you messed up the calculation, you got negative 2.5 or something like that, something pretty far from it. At least you get some points for having a negative z-score. At least it's logical. But I'll say maybe we should look at the 8.1 difference, and it should also stand out as not being logical. But at least it's logical that you could have a negative z-score. Let's say negative, let's make it closer, negative 0.95. So you didn't get the right answer, but your logic is right, and it's not too far. It's less than one standard deviation below the mean, and it is because there's a difference of 7. So if you got something like negative 0.99, you're only going to get a little bit off because it's logical. It's within the range of logic in terms of the standard deviation. It's negative. At least your thinking's there, and then you just pushed a button. This is not a button pushing class. If you're off by that much, you're going to get a little bit off, but not a lot off. However, let's say that you got a positive 0.86 for your z-score. You're going to get a lot more points taken off of that, even though the calculation's probably right, because you got 0.86, you just didn't have the negative sign, but it's illogical. That's a worse error, because you can look at the problem, and you can see that the mean is higher than the score, so it has to be a negative z-score. So make sure that you do this quick little double checks. It will save you points, and it will save you some frustrations too, because sometimes you'll go through a problem and then all of a sudden you'll hit a roadblock. And then if you look back, you think, oh, there was something that didn't make any sense. And I just went forward because all I wanted to do is just rush and finish the problem. And so double checking logic stuff will get you points and will save you some frustration. And again, if you kind of know this stuff, you can fast forward, but we will give some examples. And so I want you now to do this on your own. So we have a raw score of 145. So somebody got a score on a test, let's say 145. The class's mean was 123. The standard deviation for the class was 14. So calculate the z-score and then draw it on the normal curve. Pause, solve this on your own, continue when you're ready. Okay, you should have solved this on your own. So the first clue that we have right away is, should this be positive or negative z-score? Should be a positive z-score because the score is higher than the mean. It's above the mean. Oops. I guess I had this so I would draw in class. So I'm going to calculate this. No problemo. So what you should do is you should get in the habit of having all your logic showed in the problems that you're solving. And so the homework, you get all the points if you just make an effort. So I'm not going to catch those things if you do it on your homework. But I will catch these things on the exams. And if you don't show your logic on the exams, you're actually going to get less points. So we just gave that example of somebody who had a negative 0.99. But let's say they show their logic. They have the formulas, they show their logic, they plug in the numbers, the number made sense. They're going to get more points than somebody who doesn't have the formula, doesn't have the calculations. All they have is, that I can see, is the final answer of negative 0.86. Guess what's that going to get you? It's going to get you a big 0 if you don't have the formulas and you don't have your calculations, because I don't care what the answer is because computers can do this anyway. I care what your thinking is. So I'm going to try to model what you're supposed to have, but certainly I'm going to make some mistakes here and there, so bear with me. So Z, we need a formula, and so it's the score minus the mean over the standard deviation. So we care about the distance of the score from the mean, but we have to standardize it by dividing it by the standard deviation. So we have 145, 123. The score was 145. The mean was 123. And we have a standard deviation of, what was it? 14. I'll have to get my calculator in a second. So it's a positive z-score because remember we had a score above the mean. So that makes a lot of sense. So we have 22, correct, divided by 14. And that's going to be 1 point something. I'm just going to calculate it because it's kind of late. It's 11 o'clock and I'm doing this stuff. And so we have 22, whoops, 22 divided by 14, 1.57. So we have 1.57. That's our z-score. I recommend circling the final answer. That would be really nice. And I'm just going to double check this. So 6, 8, 14. Yep. Now I have a lot of confidence that that's the right answer. There we go. Okay. The pen should be working. It was giving me a weird, whoops. It was giving me a weird looking thing for a second. I'm gonna erase that, turn the pen back on. And again, don't worry about how well you draw. You can see that I'm drawing my laptop. It's not gonna be perfect. Whoops, this is the mean. Pretend that's a straight line. Mean's in the middle. One standard deviation above the mean's roughly here, 1.57, roughly here. Again, don't worry if you don't have an exact place. This is, I'm just guessing too. So this is a z of 1.57. So that score is pretty good. There's few scores above it. There's going to be quite a few scores below it. So make sure you have your formula. Plug in your numbers. So the thing is, if I can see you plug in the numbers, you can often get points. Where the problem is that somebody just jumps to, let's say, 22 divided by 14. If that's messed up, I have absolutely no idea how you got those numbers, and it's hard to give you credit because I have no idea how you plugged in the numbers. So if you do a miscalculation, at least I can see that you've got this right. You knew what the formula was. You knew that you had to plug in the score and the mean and the standard deviation in the right spots. You just did some sort of miscalculation. You're still going to get quite a few points, as long as it's not negative. If you come up with a negative z-score and don't catch that, that's a logical error. You'll lose more points. But if it's a positive z-score, especially the one that's between 1 and 2, it's a very logical answer. You just push the button wrong. Okay, so let's go on. So hopefully that's pretty understandable. I think it's relatively straightforward. It's a relatively easy thing. Once we start drawing things and calculating it, kind of makes sense. And so the first thing we're going to do is percentiles. And so what is a percentile? And I'm just going to draw it, because that's probably easier than just talking about it right there. Yeah. So we know we have a normal curve. Just give me a second here. I have to highlight the page. So we have a normal curve, and we know that there are certain percentages along that normal curve. We've seen that in that nice little multicolored thing, and we know that the mean is here. And actually, once you know the mean, you know one thing for sure is that 50% is over here. There's 50% of people scores over here, and there's 50% above it. So the mean splits in a standard normal curve, splits the percent of people in half. So one percentile that we know already is 50. The mean is at the 50th percentile. Well, how do we know that? We know that 50% of people are over here. They get scores below the mean. I'm trying to shade this. It's a little difficult with this laptop. But if we shade this area, we know that 50% of people are below the mean. And actually, we know that 50% are above it too. But percentile is below. So percentile refers to what percent of scores are below that score. So if we're talking about IQ, and IQ has a mean of 100, so if you got a score of 100, your score is at the 50th percentile, because 50% of people scored lower than you. And percentiles are nice because they're pretty logical. So if you have a negative z-score, so our mean is here, and you get a negative z-score, there's going to be a percentile over here. Automatically, you know that that percentile is going to be less than 50. So one of the logical things in terms of percentiles, because percentile is the percent of scores below a score, if you have a negative z-score, that's below the mean. Therefore, the percentile for a negative z-score has to be below 50. So again, if you do a miscalculation, but it's something that's reasonable, negative z-score is below 50th percentile, makes sense. You just did a miscalculation. You'll get quite a few points. And then the same thing is true for above the mean, and I think I'm going to erase this. So we have a tabula rasa, a blank slate to write on. Here's our mean. So the positive z-scores are over here. So if you get a positive z-score, you know, for one, here's their percentile, and I'm going to shade these areas. So when you draw these things, it's important to shade the area, and then this shades all the way to the tail. I'm discovering shading is more difficult than anything else in this laptop, but basically everything to the end is shaded, because there's some people over here, right? There's very few people, but there's a few people over there. So if you have a positive z-score, you know that your percentile is going to be greater than 50. And you can kind of see this right away from the shading. I look at this, if I shaded it right, if I get a positive z-score and I get something that's below 50 in the percentile, it should stand out to me like, hey, this doesn't look like it's less than 50. This should be more than 50. So drawing these graphs will help you learn, will help you communicate your logic to me, and maybe will help you double check your answer. Because if your shading looks weird, if you came up with a percentile of 20 in this, you better say something like, that makes absolutely no sense. I've just colored most of the distribution. So it's definitely not 20. It's definitely something greater than 50. So percentile is the percent of people below the score that you get. And we can say very specifically what the percentile is for any score as long as we're on a standard normal curve. And that's what we're going to assume for all of this lecture, is that we're on a standard normal distribution. I told you that the appendix that you can use for the z-score stuff will be later in the PowerPoint, and here it is. So if you want to use your textbook, it's appendix B1. And if you screamed out bingo, that's a really weird joke. Maybe your grandmother's in the room and she screamed out bingo when I said that. So B1 is the appendix. And what you want to do is you can look at it, but if you find that that table is more confusing because there's actually 4 columns in it, the table I'm going to use online is a bit simpler. So again, we know that we had that multicolored distribution that had the percentages between the mean and standard deviation. So given that, we know what the percentiles will be. Actually, I'm going to go down here. So if you have a z-score that's +1, so we're right here, we know that, right? So we know there's 50% of people below the mean. So all we have to do is for a standard deviation that's 1 above the mean, a +1 z-score, all we have to do is take 50 and then add 34.1. And we know at this line right here between the green and the yellow, the percentile at that score, 1 standard deviation above the mean, a z-score +1, would be 84.1%. 84.1% of people score below this line right here. We could also do the same sort of logic. Let's say a -1 standard deviations. So -1 standard deviations, we actually know that there's 50% from the mean to all the way to the left end, all the way at the end of the tail on the left, the low scores. But we know that there's, if you're -1 standard deviations, there's 50 to the mean. If we take 50 minus 34.1, guess what the standard deviation, or I'm sorry, guess what the percentile is here? It'd be 50 minus 34.1, which would be 0.9. I'm just going to do it in my head. 5, that would be 15.9. So there's only 15.9% of the scores below this score. So this is at the percentile. The percentile is 15.9 percentile for this score. So using this logic, we can easily figure out for any score. Sorry about that. So we're going to start off by finding percentiles. So now we already know how to do the z-scores. Now we're going to do the percentiles. And we're going to use the table. And what I'm going to show you is this table I'm going to use is really simple. So it breaks up. I can't afford a Lexus, get off of there. I can afford Roku, so that's better. I like this table because it splits it up into 2. So negative z-scores is in one table. And if you ever forget where you are, it just shows you. You're below the mean. You're over here. And what this table will tell you the percentile, the percent of people who are below any score. So any z-score that you give, this is the percent of people who are below it. And we're going to get into how to do it. I think it's better to have an actual score, but I'm just showing you at first. There's so many ads here. This is the positive z-score table. So if you have a positive z-score, you go to this table, and it will tell you the same thing. It will tell you the percentile. If you notice, the positive z-score table has numbers above 50. Kind of look here, we start with 50 and they get bigger as we go down. And then the negative z-score table starts at 50 but goes below 50. So the percent of scores, the proportion of scores below a negative z-score is going to be below 50. So let's do some examples, because I think it's good to have some concrete examples, but I just wanted to show you what's on the table. Okay, so here's a percentile answer. We're going to work through it real quickly. So we already know how to do the z-score, right? We take a score, we subtract that score. We take that score, we subtract the mean from the score. So if you get a score above the mean, you have a positive z-score, below the mean, negative z-score. Those are just in points. Points don't matter. What matters is standard deviation. So we take that difference, we divide it by the standard deviation. So that's how we get our z-scores. So I'm going to first draw this one. The z-score is 0.40. So while I'm doing this, I'm going to ask you the question, 0.40, where should this z-score be? Should it be above or below the mean? 0.40, that is a positive z-score. So it's going to be above the mean. So again, this is kind of rough, but that's okay. And we know the mean is here. And a z-score of 40 is going to be around here. So z-score of 0.40 is going to roughly be maybe around here or so. Again, you don't have to be really perfect. I'm not being perfect on this. I'm just making a rough guesstimate. So what I want to say is draw out the thing you're trying to find. So this is asking you for a percentile. A percentile is all the scores below this z-score. So shade that area. So shade that area, and this is the number you're looking for. You're looking for a percent here. And if you know this, if you see this shading, what should your percentile be? Should it be above 50 or below 50? It's above the mean. We look at this shading. The shading is actually taking up at least a little bit more than half of the picture, so it's going to be above 50. So the chart's going to tell us 100% specifically where we are. So I'm thinking about what to do here. So we need a positive, so make sure you're in the positive. If you make a mistake and you do it in the negative, you're going to have a percentile that's below 50. Hopefully you'll catch it, go to the right table. Also, if you look at this, if I kind of look at my drawing, which is imperfect, but you know, it's above the mean and there's a little bit more space filled out, well, this kind of looks like what I'm looking for. So this is the right table. What I'm going to do is I am going to snip this because I want to draw on this. And I'm going to have to say, see you later, drawing. And I'm going to snip this little table real quickly. I'm going to draw the whole thing just so that we have the whole thing. We're not going to use the whole thing, but at least you can see it. Okay, there's not really anything much complicated to this. Over here, we have the first decimal point. So 0.1, 0.2, 0.3, 0.4, they're all positive. Remember, they're positive z-scores. 1.1, 1.2. But when we calculate z-scores, we want to go to the second decimal place, so the columns are the second decimal place. This one's kind of easy because we had 0.4, correct? So 0.4, 0. So remember our z-score was 0.40. So all we're simply going to do is going to go to 0.4. The second decimal place is 0. So that's our proportion. So the only kind of complicated thing here is that this gives us a proportion. So the proportion is there. If we want a percent, all we have to do is take the decimal place down two spaces here. So this one, I'm going to just write on this. This is nice. I can write on this table. 65.54. So round off everything to this second decimal place, and it's a percentile. So all this is saying is that at the z-score, so So here's our mean. 0.4 we said was roughly here. So z-score, that's 0.4 above the mean, and we are curious about this percentile over here. This shaded area has 65.54% of people. So 65.54% of people got below this score. They're in the shaded area. Below this score of 65.54% of people, that's the percentile. And we got it from this number right here. So it says 0.65542. It's a percent that we want, percentile. So all we do is move the decimal place to 2 places, and so it's 65.54. So hopefully the chart is pretty easy. It's just a matter of looking up the z-score in the chart. So let's go to the next example. Oh, so see, here I did this. I think I actually made these, this table from this example from another table. So regardless of what z table you have, as long as some joker didn't put up something that's wrong to mess up people in stats class, any legitimate z-score table is going to give you the same number. I got this from another table, probably from another stats book back when. Okay, I want you to do this one on, oops, I was going to have you do that on your own, but I think I have a couple more. So let's just do a negative one on our own. Let's take you through both. And I think I have 2 other examples that follow this. So we'll have 2 examples that you'll do on your own. So the percentile here is negative 1.20. So if we draw this to help our answer, and I would, again, I'm not just going to say recommend, I will require you to do this, because if you have this thing, it shows me your logic, you'll get points. If you don't have this thing, you aren't showing me that you know what's going on. So we have a really horrible normal curve, but that's okay. Doesn't really matter because we're trying to convey our logic. I don't know why it's blinking. And then the bit distracted by the blinking. I was wondering if my battery's low, but it's not. I'm plugged in. So negative 1.24. I'm sorry, negative 1.20. Brought the 4 from the other one. So going down here, maybe around this area. Again, you don't have to be perfect on this. So this is a z that's negative. Sorry about the blinking. We're almost done with this, so I'm just going to put up with this. Sorry about this. I lost my concentration again. That's a 2. Silly thing. Stop blinking. I hope this isn't giving people epileptic seizures. So we want this area. This is our percentile. It doesn't blink if I'm doing this. Maybe because I had this drawn over there. So we look at this, and we know right away the percentile is going to be what? It's going to be below 50. And again, it should make sense because we're below the mean, but also it should make sense because we look at this table and it's very obvious, I'm sorry, this chart, and it's very obvious it's going to be less than 50. So let's go ahead, negative 1.2. We're going to look at the chart now. If you make a mistake and start looking here, you're going to get things that are above 50. So that is one double check. You say, whoops, I was on the positive. I need to go to the negative. The thing I drew looks more like this. And so I'm going to snip this so I can draw. Just keeping it simple. So it's negative 1.2. So we go here first. So we always start over here. Negative 1.2, and it's the 0. 1.20. So our percentile here is 11.51. 11.51 percentile. If you do this little abbreviation, make sure you have that little ILE there. So it says 0.11507. So move the decimal point 2 spots for something that is expressed as percent. So percentile is percent. And so it's 11.51. We round up here to the second decimal place. What I'm going to say is, let's say it was negative 1.24. I'm going to erase this because you're in the way. Numbers and letters. Let's say it was negative 1.24. We would start at the same place, negative 1.2, that's the first decimal place. But then we have to find 4 over here for the second decimal place. So if it was negative 1.24, our percentile would be 10.75 percentile. So negative 1.2, we start here, and then we go to the right till we find the 4, which is the second decimal place. So hopefully this is relatively easy. You know, I hope all stats sort of go like this for you, is that when you see it first, you think, oh my gosh, what does this mean? Look at that chart, it's got so many numbers, but it's just really just follow that recipe and we can find it. So let's do 2 examples on your own, and I'll give the answers also. So do this one. You have a z-score of 1.86. So what's the percentile? My first recommendation that you draw the diagram first and then go ahead and go to the chart. Go ahead and do this and use the chart to solve this question. Okay, you should have solved it already. I don't have the answer here. I have to do the answer myself. So I'm going to draw. It's 1.86. So what do we know right away? A z-score of 1.86. What do we know right away? It's above the mean. And so it should look something like this. So we have our normal curve. We have the mean in the middle. It was 1.86. It was a positive z-score. We know it's above the mean. And we know 1's kind of here maybe, and 2's kind of here. So it's probably, you know, roughly around here. Again, I'm not going to grade you on location because it's a rough estimate. 1.86. So a z-score of 1.86, and we're doing percentiles. So shade and show me that you know what you're trying to find. If you just draw this and you don't shade it, it doesn't show me what you know in terms of what you're looking for. You're looking for the percent of people in the shaded area. And looking at this, we know that our percentile needs to be what? It's going to be greater than 50. You know, you should know that right away when you see it's above the mean, but then if we look at this, it should just slap you in the face and say the percentile has to be above 50 for sure. And so let's go to the chart and find the z-score of 1.86 and answer this specifically. So I'm going to go to this chart. If you're using the chart in the textbook and you're using different techniques to find this, what I'll say is you're kind of on your own, but you can double check your answers. So positive z-score, this looks like the thing that we just drew, correct? So we know it's positive z-score, and also that diagram looks kind of like what we drew. And thankfully it fits well on this screen. So I'm going to snip this, and I'm going to snip everything that is on the screen, and I'm going to expand it a bit so you can see just a little bit better. So it was 1.86. Again, if you get the wrong z-table and you start getting numbers here that are below 0.50, you know that you're on the wrong table because you know it's supposed to be above 50. So 0.86, I'm sorry, 1.86, we start here. So our first decimal place goes to 1.8. And then our second decimal place is 6. So 1.86. If I can draw it. If you go off the border, it won't draw for you. So 1.86. So we go over here and we find it right here. And so 1.86. And this percentile is a whopping 96.86. So almost 97% of people get scores below a z-score of 1.86. And that should make some sense. If you go back to the multicolored diagram, if you look up the positive, 2 standard deviations above the mean, you're going to see that this number is just a little bit below that one. So here's our percentile. So let's do another example. But I'm hoping, just sort of talking through this and drawing this, that this is relatively straightforward. Here's another example. So we have a negative z-score in this case. So take the negative z-score, so negative 0.77. What is that percentile? So the first step to find the answer is I'd like you to draw that chart, because that tells me that, for one, you know what you're doing. For two, it will help you think logically in terms of what kind of answer you need, and will serve as a good double check. So go ahead and solve this, and when you're done, take it off pause, and we'll go over the solution. Okay, you should have done this already. And so we have a negative 0.77. I'm going to draw it. That's my first step, correct? And this is to show my logic, and it will help me double check my answer. Oh, that's really severe. That's okay. This is not a drawing class. So here's our mean, and we have a negative 0.77, so maybe somewhere around here roughly. So we have a z-score of negative 0.77. And we're curious about the shaded area. So we're curious about what percent of scores are below this. This looks like the state of New York a little bit. And one of my graduate schools that I went to was Cornell, and Cornell is in Ithaca, New York, and it's right here in the middle, centrally isolated, as they would say. But it has nice rolling hills and waterfalls all over the place. So it kind of looks like the state of New York. So once we look at this, we know for sure that our percentile has to be below 50, correct? So a score that's below the mean, the percentile is going to be below 50. If we look at this state of New York, it's going to be below 50. So let's go to our table. If you accidentally use the positive z-score table, it should jump out to you because you're starting to see numbers above 50. You know that's not possible based on what we just drew. So we go up here, and this doesn't look like the state of New York, but this looks more like our chart, negative z-scores. And I'll highlight this, and we'll find the percent of proportion. This gives proportion. That's why you have to take 2 decimal places down to get a percent. So let's find out what the proportion of people is at negative 0.77. So I want to double check that, negative 0.77. So we start off here, our first decimal place is 0.7. So negative 0.7, it's right here, and it's negative 0.77, so we want second decimal place to be 7. So we go down this little thing, and we go over here, and our answer is the percentile at that z-score of negative 0.77 is 22.07. So 22.07% of the scores are below that z-score of negative 0.77. So here's our percentile. Again, percentile tells us the percent of scores below this score. This one is a negative 0.77 z-score. So hopefully this is pretty easy so far. And so what I'm going to do is I'm going to stop this. And this will be the first part of the lecture. And so we will continue with the second part of the lecture in the next video.